second speaker for this session is Professor Mark Van Raamsdonk from University of British Columbia, Canada. And Professor Raamsdonk is also a leading expert of gravitational physics, string theory, and black hole physics. Particularly, he has very valuable and important contribution to the physics of holography and ADS-CFT. We all know that how important his contribution in ideas related to quantum information and space-time. So today, I request Mark to share his seminar, and let's start. Yes, Mark, you can start.
Mark, we cannot hear you.
I think it's muted, Mark. Yeah.
Okay, how about now?
Yeah, clear.
Yeah, we can.
Yeah, I moved the toolbar to the top. I must have closed that. Okay. Yeah, so I'm happy to talk about this topic that I think is appropriate to the meeting. Thanks a lot for the invitation. This work will be actually some work that should appear soon in the next couple of weeks with Brian Swingle and my student Peter Simidja and Brian's student Stefano Antonini, and also based on earlier work by myself and this previous paper with these authors. And so I'm going to talk about a string theory approach to quantum gravity, and in particular focusing on the ADS-CFT approach, where we have the emergence of space-time and gravitation from the strongly coupled physics of quantum field theories. And so this approach to quantum gravity, I think, has taught us valuable lessons about black holes, and lately about the emergence of space-time from quantum information ideas, from entanglement of degrees of freedom, and also even about the emergence of gravitation from the physics of entanglement. But one of the things that we want to do with quantum gravity, one of the reasons for studying quantum gravity, would be to understand better the physics of cosmology. So in order to really understand cosmology and the Big Bang, then we should presumably require a quantum understanding of gravitational physics. And this is a place where I think the ADS-CFT correspondence and string theory have had, I guess, more difficulty. Okay. And so one, I would say, possible misconception is that maybe the reason why it's been difficult to understand or to apply ADS-CFT to cosmology is that ADS-CFT usually works for describing spacetimes that have negative cosmological constant. And we might say that we see our universe has positive cosmological constant. But I think we should be a little bit careful here, because that's really not what the observations tell us. The observations tell us that our universe has an expansion which is accelerating at the present time. So we have some scale factor in the universe that might look something like this. So currently we're in a phase of acceleration. And if we just take that, that piece of information and plug it into the Einstein equations, then it tells us something about the matter in the universe. It tells us that 3p, 3 times the pressure plus the energy density, is negative. And so the simplest way, perhaps, to write down some model with this being satisfied is to take a positive cosmological constant. But it's really not implied by this, and it's not the only way to theoretically get this acceleration. Another very simple possibility is that we could have some time-dependent scalar fields in our universe, and that the potential energy of these scalar fields is currently positive and dominating the expansion. This has the same effect currently as a positive cosmological constant. And so we really have, just from the observations, either of these could be possible explanations. In fact, case one is, in a sense, a special case of two, where the scalars are just at, say, some minimum of their potential with v greater than 0. Okay, so case two is just the case where they might be changing with time. Another reason why we might want to consider the possibility of scalars having a time-dependent background is just that the cosmological space-time already has this time dependence in the metric. And if we want to consider the most general background that is consistent with these symmetries that are already preserved by the cosmology, then you would in general want to consider time-dependent scalars. They don't break any additional symmetries. And so one might think it should be generic to consider them in the context of cosmology. So if it happens that this acceleration that we observe is because of some potential energy due to scalar fields that are time dependent, then it's not really clear what the cosmological constant should be. So the scalars would be rolling down some potential. If you look at the equations that they satisfy, the potential will be decreasing with time, and they may well be rolling towards some nearby extremum which has a negative value of the potential. And we might call that the cosmological constant. Okay, so this is all in the future of our current universe. So observations really can't tell us where the scalars are headed. So to summarize so far, our observations that our universe is accelerating could be explained by a positive cosmological constant, but it could also be explained by having a potential energy of scalar fields that are time dependent. And in this case, the cosmological constant, which we could define to be some nearby extremum of the potential that perhaps the scalars are rolling towards, that could be positive, it could be 0, or it could be negative. So if we want to try to understand cosmology from string theory or ADS-CFT in order to come up with some kind of microscopic model of cosmology, we can look at these different possibilities and ask maybe what should be our focus? What should the theory, where should we direct that? Okay. And if we look at the current understanding of string theory, then the second possibility overall is quite natural, because in the effective field theories that come out of describing string theory compactifications, there are generally plenty of scalar fields in the game. And then perhaps more importantly, so far in our understanding of string theory, we have a beautiful microscopic understanding of spacetimes with negative cosmological constant using holography. And we've had much more difficulty trying to actually even show that there are stable spacetimes with lambda greater than 0. And we don't have any examples where a 4-dimensional gravitational theory with lambda greater than 0 has a microscopic description. So there seems to be some kind of technical obstruction to that. So to me, it seems like a logical next step. I mean, even if it turns out that our universe does have a positive cosmological constant, but based on how we understand the theory at the present time, it seems like a logical next step in exploring cosmology from a microscopic point of view, in trying to come up with microscopic models of cosmology that might be similar to our universe. I would say this lambda less than 0 possibility is a good target. So even though a lot of the string theory discussion does seem to focus on the lambda greater than 0 possibility, I would say we should spend more time, maybe at present, thinking about the other lambda less than 0 possibility, because I think at this point, we have a much better chance of coming up with some microscopic description of that. Okay, well, so we're going to focus on this possibility. So supposing that the fundamental cosmological constant is negative, and perhaps we have some time-dependent scalar fields, can we actually come up with a microscopic or holographic description? And it's unfortunately is not very obvious how one would do that, because even though ADS-CFT allows us to describe many spacetimes with negative cosmological constant, they're not really the kind of spacetimes that we want for cosmology. So in cosmological physics, we have matter and radiation that fills the universe, that's homogeneous and isotropic. Whereas the kinds of spacetimes that we can describe in ADS-CFT, these are spacetimes that asymptotically are empty. So we could have vacuum ADS spacetime. We could add lots of interesting stuff in some region of the spacetime. We could have black holes, gravitational waves, radiation, etc. But far away, the kinds of spacetimes that we describe using ADS-CFT are asymptotically ADS. So out far away, there's no matter. And so the question is, well, how do we describe a universe that would actually be filled with matter like we expect in cosmology? A different way of looking at the challenge is just to start with the cosmological spacetime that has lambda less than 0. So look at, say, lambda less than 0 plus radiation or plus matter. What do those spacetimes typically look like? Okay, so they tend to be Big Bang, Big Crunch spacetimes, because as the universe expands, this negative cosmological constant becomes more and more important as matter and radiation dilute, and eventually that causes the universe typically to recollapse. So a very simple explicit example of lambda less than 0 cosmology would be just to add radiation and assume a flat metric. And then you get this simple analytic scale factor. And so you see you have the cosine function in the square root of the cosine is the scale factor. So you have a Big Bang, Big Crunch, which is symmetrical. And if you want to understand the causal structure, then it looks like this with past and future singularities. Okay. So we notice that this kind of spacetime, even though it has lambda less than 0, it doesn't have any asymptotically ADS regions. Okay, so there's not an obvious place for a boundary or boundary degrees of freedom or a holographic description. So this is where I think maybe one would get stuck. But there's actually a hint for perhaps how to proceed. Okay, so the hint is that even though this cosmological spacetime, it doesn't have any asymptotically ADS regions, if you actually consider the analytic continuation, so imagine complexifying this time coordinate and then consider imaginary values of the time coordinate, then the analytic continuation of this spacetime is the spacetime with a Cauchy function here. It's a Euclidean spacetime that for large and small values, plus or minus, as you go to plus or minus infinity in the imaginary time, in the Euclidean time, then you reach asymptotically ADS boundaries. So somehow hidden in the complexification of this cosmological spacetime, you do find an appearance of these asymptotically ADS boundaries. And so far, that's kind of a mathematical observation, just that there's some Euclidean spacetime that's asymptotically ADS that you can get by this mathematical operation from the Lorentzian spacetime. But in quantum field theory, and even sometimes in quantum gravity, Euclidean spacetimes or Euclidean versions of the theory play an important role. So if you have, let's say with quantum field theory, if you start with a Euclidean quantum field theory, then this is often used to define a natural state of some associated Lorentzian theory. So the vacuum of a field theory on Minkowski space has observables that are just analytic continuations of observables in the Euclidean version of the theory. Okay, so we could say
Mark?
the Euclidean, yes.
Yeah, can I ask a question?
Yes, please.
Yeah. So, I mean, the example that you provided, it only works for that simple radiation and flat slicing. But suppose we have both radiation and matter, then the scale factor would not be that simple. And there may not be any analytic continuation to the Euclidean domain. So then how do you propose that there will be asymptotic ADS regions?
Yeah, so actually it's reasonably general to get asymptotically ADS regions. So if you have an equation of state, so if the dependence of the energy density on the scale factor is some relatively simple kind of function with matter or radiation or a combination of these things, then it's still true that you have some analytic continuation, and it's still true that you have asymptotically ADS regions. So this is fairly general, provided basically all you need is the equation of state. The energy density should decrease as the scale factor increases. So as long as you have ordinary kinds of matter that dilutes, and then also if you have some time-dependent scalar fields, then they should also preserve this time reversal symmetry. Okay, so you could have models also with scalar fields. And so for this fairly general class of situations, then you do find that an analytic continuation exists. You can basically see that at the level of the differential equations. For the scale factor, there's an analytic continuation of the equations that's sensible, and then you can solve them and show that the asymptotic behavior is similarly an exponential increase. So I'll restrict to these cases, which are fairly general. So a wide class of models of cosmology with lambda less than 0.
Maybe I will ask
can I ask something just now? Yeah, okay.
Sure, yes.
Now, is it possible to have a lambda in higher dimensions which is negative and effectively in 4 dimensions it's positive? When would that work?
So yeah, I mean here, right. So I mean, it is possible sometimes to start with some higher dimensional gravity theory and then find, say, some compactification of that that ends up being a negative cosmological constant. At least, sorry, yeah, I guess in some cases it is possible that in your effective lower dimensional theory you get a cosmological constant that is one sign or the other. Here I'll mostly be thinking about just the 4-dimensional description. So I won't worry too much about what some higher dimensional theory might look like.
Okay, but the lambda that you were talking about in ADS CFT has a negative value in the bulk, right?
That's right, yes.
So that's why I'm asking this question, nothing. And that's a high dimensional bulk, right?
Oh, I'm sorry. You were, okay. I think I was confused about your question. So you were talking about the underlying CFT.
Yes.
I see. Okay. Yeah, I mean, my underlying CFT will just live on a lambda equals 0, like a flat background.
Okay.
But let's let's get there in the next slide.
Okay.
Right. Okay. So standard, textbook quantum field theory, we can take the Euclidean theory and say the correlation, the 2-point function in the Euclidean theory analytically continues to the vacuum 2-point function in the Lorentzian theory. So Euclidean theory, in a sense, naturally defines a state of the Lorentzian theory. This also comes up in the Hartle-Hawking approach. If you take the Euclidean gravitational path integral, then their idea was to use that to define a natural state for the cosmology, for the Lorentzian cosmology. Okay. And so basically, this is what I want to do here. We start with this observation that there's some natural Euclidean space-time that is associated with our cosmology. What I want to do is basically use this, use a physical theory on this Euclidean space-time to construct a state for the cosmology. So I basically want to do a Hartle-Hawking type idea here, except instead of the no boundary proposal of Hartle and Hawking, you see my Euclidean space-time, it does have a boundary. It has a boundary in the Euclidean past, which is an asymptotically ADS boundary.
Hi, Mark. Can I have a question?
Yes.
So this is regarding this metric which you have here.
Yes.
Since you have radiation, I would have expected that there should also be a t to the power half kind of a behavior, like overall. So your h here, is it a constant or is it time dependent?
So this is just it's just a constant.
Then
with
these
lambda less than 0 and radiation, then this is the solution. So a is the square root of the cos of ht.
Okay. So because in some limit it should get t to the power half.
So like a squared is what's in the metric, right? So a is the square root of the cos of ht. So indeed there's a square root there.
Cool.
Yeah.
Okay, thanks.
Okay. Right. Okay. So yeah, I want to use like this Euclidean gravitational theory to define a special state for the cosmology, and is different from Hartle-Hawking because I have an asymptotically ADS boundary. And the other difference from Hartle-Hawking is, well, Hartle-Hawking, relies on a gravitational path integral that we don't completely know how to define. Okay. And so in my case, I have an advantage because even if we don't know exactly how to define this gravitational theory on the 4D Euclidean space, at first, well, we can use the fact that it has an asymptotically ADS boundary and then give a precise definition of the gravitational path integral by some dual CFT path integral. Okay, so that is the goal here. I want to find a holographic description, so holographically define this gravity theory on the Euclidean space-time, then use that to define a special state for the cosmology. And so in that way, I'm going to try to come up with a holographic description of these lambda less than 0 cosmologies. So the pictures on the left here summarize what we have so far, that there's a Lorentzian space-time with a big bang and a big crunch. Now I'm going to consider just somewhat more general space-times where the scale factor is time symmetric, as I mentioned, but it could be from radiation or matter or radiation plus matter. It analytically continues to a space-time here that has asymptotically ADS regions in the Euclidean past and future. So I'll call this sometimes we call this a Euclidean wormhole space-time because it connects these two boundaries. And then one thing I want to point out, because I'm considering a flat cosmology, I'm focusing on that case. So this Euclidean wormhole also has some translation invariant directions. And if I do a different analytic continuation along one of those translation invariant directions, I get to another Lorentzian space-time, which I would call a Lorentzian wormhole. So it's a static space-time with two asymptotically ADS boundaries, and it's related to these two other space-times by analytic continuations. Okay. So the plan now is actually, I'm going to first try to describe a holographic description of the space-time on the right, and then we'll go back and understand the holographic descriptions for the other two. Okay, so now we're focusing on this static Lorentzian wormhole space-time with two asymptotically ADS boundaries. So the two asymptotically ADS regions suggest that the holographic description involves two three-dimensional holographic CFTs because my bulk geometry is four-dimensional. Okay. So this is a little bit like Maldaceno's suggestion for the holographic description of the two-sided black hole, where you have two 3D CFTs that are entangled with each other. But in this case, the space-time is traversable from one side to the other. It's a static space-time. So someone could actually just start over here and then end up over here and then go back. And so that means that you could send a signal from one boundary to the other and back. And so we would say from the CFT point of view that these CFTs must somehow interact with each other. Okay. You could perturb one CFT and you should be able to feel the effect in the other CFT. So it's not enough for these CFTs just to be entangled with each other. They have to be interacting, but the interaction should be not just a regular local interaction. So it does take some time if you perturb one side, take some time for the signal to go across to the other side. And so that suggests that even though these CFTs might be interacting, perhaps they're still separated somehow physically from each other. So this all suggested an idea that maybe these CFTs are interacting through some auxiliary theory, which is a higher dimensional theory. So the basic idea is that we're going to start with a pair of these holographic CFTs. On their own, they would be dual to asymptotically ADS for spacetimes. If you just entangled those two CFTs, they could be dual to a two-sided black hole spacetime, but that would be time dependent and not traversable. And so now I'm going to consider something stronger, which is an actual interaction where the two 3D CFTs are coupled at two boundaries to a four-dimensional CFT. And now I want the entire space-time, I want the gravity dual of this whole thing to still retain its four-dimensional character. I don't really want to define a five-dimensional geometry. And so I'll try to keep this 4D CFT not holographic. So that one will have just a relatively few, number of degrees of freedom, whereas the 3D CFTs are going to be full holographic CFTs with lots of degrees of freedom. So let me motivate why it is that we should believe this could be dual to this picture. I mean, I've already given some motivation. I'll just mention a couple of other motivations. So theories with boundaries or defects have been considered in the context of ADS-CFT before. And the simplest example is if you have a 4D theory with two three-dimensional defects. And it's understood that the defects in the bulk correspond to branes in the geometry. And there's one case where these branes naturally connect up with each other. And that is if you choose a certain kind of defect and then it's mirror image. So often if you have a supersymmetric 4D theory, there's some kind of defect that would preserve supersymmetry, and then a mirror image one where together the two things might break supersymmetry. And in the bulk, this is reflected in the fact that you have a brane anchored to the boundary here, and then the corresponding anti-brane anchored to the boundary here. So this top solution in that case would be unstable because it's a brane anti-brane pair. And what tends to happen then is that the branes join up in the bulk. So that's kind of a probe version of what we want. We want to have, instead of the defects, we want two boundaries. We want these boundaries to have lots of degrees of freedom. But I want to think maybe of the 4D geometries as behaving like one of these brane anti-brane pairs. So we have a 4D geometry related to this 3D theory at the top, and another 4D gravitational theory related to the one at the bottom. And then the picture would be that, again, because of the physics, like this brane anti-brane physics, they want to join up in the interior. Okay. A different way to understand this is just from a field theory point of view, where we start with this pair of decoupled three-dimensional CFTs. So that itself defines some product CFT in the UV. And then we couple those two things. And so this coupling with the 4D theory is some kind of perturbation to the UV of this quantum field theory. And we might expect that this induces a renormalization group flow that ends up in some other three-dimensional theory in the infrared. So it's possible that 3D theory in the infrared is also a conformal field theory, but maybe more generically, the 3D theory that you flow to in the infrared is going to be one which is confined. Okay, so it would be a common endpoint of a renormalization group flow to have confinement rather than a conformal theory. And so this is an interpretation of what we're seeing here in the gravity picture. The fact that the two four-dimensional geometries connect up in the infrared means that there's only a certain finite distance I can go into the infrared before I hit this joining point, before I hit, in a sense, an infrared end of the space. Okay, so the geometry picture is consistent with the fact that the idea that this is a confined theory in the infrared. Okay, and in these kind of brain scenarios, you could also understand from the field theory point of view that this joining up of the two parts, it's related to a symmetry breaking that happens in the field theory. If you have a global symmetry G in each of those two CFTs, that would be related to a gauge symmetry or a gauge field that lives in this gravity theory on either side. But then because there's really only one gauge field, the two gauge fields are just in this one geometry that connects up. In the end, there's only one copy of this symmetry that's preserved. Okay, so going forward, I'm just going to assume that this is the correct construction of a holographic description for this Lorentzian wormhole spacetime. Okay, so the summary of that part is that we want to take two three-dimensional holographic CFTs. We want to couple them together somehow by a higher dimensional theory. And then the proposed dual for that is that we have an asymptotically ADS geometry with these two different boundaries that connects up in the middle. So from there, I can go back to the Euclidean wormhole spacetime that I was going to use to construct my state for the cosmology. And that's kind of a trivial analytic continuation. These theories preserve a 2+1 dimensional Minkowski symmetry. And I could consider the Euclidean version of the same field theory just by changing the Minkowski spaces to Euclidean spaces here. Okay, so this Euclidean field theory is dual to the Euclidean wormhole. Okay, so just to emphasize what I said before, how you could use a Euclidean theory to define a state for a Lorentzian theory. So the way that we could understand the vacuum state in the top picture is by taking that Euclidean theory, slicing it on a surface A, and then the vacuum wave functional for the Lorentzian theory on top is defined by doing the path integral, the lower half of this path integral. Okay, so this path integral here is the integral over all field configurations below the surface A with the boundary condition that the fields on A are phi 0, the argument of the wave functional. So we see that we're using the Euclidean path integral to define a state of the Lorentzian theory, and that state is the vacuum state. Okay. So
can I ask a quick question in the
yes, yeah, good place.
In your expression for the metric for the Lorentzian wormhole, your tau is basically what is traditionally called as the proper radial distance, right?
Yes, actually, I realized this should have a minus sign. This should have a
minus sign. No. I don't think so.
Oh yeah, no, I'm sorry. You're right. Yes, yeah, indeed. The tau is the proper radial distance. Yes.
Yeah. So that's an interpretational point that you calling the tau as the proper radial distance, in some sense, right? In comparison to the Euclidean case.
That's right. So it basically, I mean, in both cases, the tau coordinate is a spatial coordinate that goes from one boundary to the other boundary. Okay,
Yeah.
and so that leads into the next point, which is that now I want to make an analytic continuation on this tau coordinate.
Yeah.
So you see, these were related, but Lorentzian and Euclidean, they were related by an analytic continuation, but of one of these x coordinates.
Yes.
Okay, and similarly, what I did to go from Euclidean to Lorentzian is slice the path integral in this way, perpendicular to that x coordinate.
Okay. Yeah.
So now what
you.
I want to do, oh yeah, okay.
Yeah.
So I'm going to continue, your question leads very naturally into the next part. So now what I want to do is understand a description of the cosmology, which is an analytic continuation in the tau coordinate. And so I will just slice the path integral in a different way. Okay. So slicing the path integral in this way gave us the vacuum state that was dual to Lorentzian wormhole. Slicing the path integral in this other way, perpendicular to the tau coordinate, that should define a state of the cosmology. Okay, so in the like on the right hand side, we just have the 4D gravity point of view. So this is like the Hartle-Hawking picture. The lower half of this Euclidean space-time is the saddle point geometry for some Euclidean path integral that is defining our cosmological state. But then we have this microscopic picture where I slice the field theory path integral. So that the dual state is defined by this path integral, and I have it on the next slide, where I consider all field configurations of this Euclidean theory below the surface B with the boundary condition that the fields on B are equal to phi 0, the argument of the path integral. Okay, so this is a funny, so the claim is that this state is the gravity dual of the cosmology. But it's an interesting conclusion because you see that the slice B, it only goes through the 4-dimensional auxiliary field theory that we introduced to couple our two 3D theories. It's going to be some complex high energy state of that 4-dimensional CFT. And it's strange because we said the 4D CFT wasn't necessarily a holographic theory. In fact, we wanted to have relatively few degrees of freedom. Okay. So somehow the cosmology seems to be dual to this complicated, some kind of complicated high energy state of the 4D CFT. And the reason I say it's complicated is that you have this Euclidean 3-dimensional theory with many degrees of freedom that appears in the path integral that constructs the state. Okay, so it's a state that is, it's not the vacuum state, it's some high energy state, and it's a very specific high energy state that makes use of a holographic theory in its construction. So we can understand this a little bit better if we, for the moment, imagine that our 4D theory is actually holographic. Okay. And so in that case, we would be talking about a high energy state of a holographic theory, which is typically dual to some black hole spacetime. And so I could draw the space-time diagram for this in this way. We would expect to have some exterior region of the space-time that's asymptotically ADS because we're talking about a state of a 4D CFT. There should be some black hole horizon. And now we could understand where the cosmology is. From this higher dimensional point of view, we would say the cosmology is living at some inner boundary of the space-time behind the horizon of the black hole. So we have a complicated state of the 4D CFT, which is dual to a black hole state. And then that can still be describing some cosmological physics if that physics is localized to some 4-dimensional surface at the boundary of the 5-dimensional space-time. So this would make use of the idea of gravity localization and the Randall-Sundrum picture of cosmology. but we don't necessarily have to have the cosmological, the 5D spacetime be geometrical. If I now consider taking fewer and fewer 4-dimensional degrees of freedom, but still keeping this 3D theory to be holographic, then the idea would be we would still have some dual description of a cosmological spacetime, but not necessarily this picture with a 5D bulk. Okay. So continuing on from that. Okay, so now we can talk about how do I extract the observables? How do I learn about this cosmology based on this holographic description? And at first, it might seem very difficult to learn about the cosmology from the holographic description, because from this lower picture here, the cosmology is behind the horizon of some black hole. And understanding about the physics behind the horizon of black holes in ADS-CFT is notoriously challenging. So it might seem that we just have this really complicated, nearly thermal state, and it would be difficult to learn anything from it. But fortunately, there's a way around this puzzle. And that is to make use of the fact that this was a very special state of our 4D CFT, which also has, so it comes from a Euclidean path integral that also defines the wormhole geometry. Okay, so let me expand on that. So we have this microscopic CFT. We said that by slicing the path integral in one way, we can define a state that is dual to a wormhole spacetime. And by slicing the path integral in a different way, we can define a state which is dual to our cosmology. But because it's the same underlying Euclidean theory that defines both of these things, it turns out that some of the observables in the cosmology, well, those you would calculate using this path integral also, and then those same quantities would have an interpretation in the wormhole spacetime. So we have these two related spacetimes, but this wormhole spacetime is a lot simpler. Okay, so because the wormhole spacetime, it doesn't have a big bang or a big crunch. In fact, it's weakly curved everywhere. So the curvature only gets, the curvature scale only gets smaller as you go out to the asymptotically ADS boundaries. And so in particular, just ordinary effective field theory should be valid everywhere if you want to make calculations about quantities in this spacetime. So this turns out to be very powerful. As an example, so basically what it implies is that if you want to calculate something in the cosmology, at least for a lot of quantities, you can calculate an associated thing over here in the wormhole geometry, and then just actually analytically continue to find the answer in the cosmology. So we've already seen an example of that. Because both of these come from different analytic continuations of the Euclidean picture, then the scale factor in the cosmology is just a double analytic continuation of the scale factor in the wormhole. Similarly, you could look at some correlation function in the cosmological spacetime. So for example, if I wanted to look at the 2-point function of the stress energy tensor in the cosmology, then it turns out that that also is just some analytic continuation of the 2-point function in the wormhole. In fact, the one I've drawn where the time in the cosmology is at the time symmetric point, that's just equal. Here we would say t equals 0, and then that would correspond to tau equals 0. And so that correlation function is actually just going to be equal to a correlation function in the wormhole spacetime. Okay. So the idea here to extract the cosmological physics would just be to calculate observables in this other vacuum static spacetime, then analytically continue them, and then interpret them in terms of cosmological observables. Okay, so let me talk about then some general predictions of this framework. So of course, the specific predictions will depend on our choice of a specific three-dimensional underlying conformal field theory and the 4D theory that it's coupled to. Once we choose those things, actually everything else is determined. So the only inputs for this entire model are our choice of 3D and 4D CFTs. I should mention then the effective field theory. So the first thing we might ask is like, what is the 4D gravity theory and what other fields do you have? Okay, so those are more like mostly determined by what our 3D CFT is. We can set the cosmological constant scale or the curvature scale. That's usually related to the number of degrees of freedom in our 3D CFT, in our dual CFT. The gauge group in this effective field theory of the cosmology would be related to the global symmetry of our 3D CFT. So we have some control over what kind of matter that we want to put in our cosmological spacetime. Other than those things, basically for all the models, we would have a homogeneous and isotropic flat cosmology because we're basically building in the R3 symmetry. Okay, so even though our observed cosmology is not completely translation invariant, we would say in this case, the idea is that at the quantum level, the full state of the universe that we're defining for the cosmology, that would be translation invariant. And that would describe, say, some ensemble of possible cosmologies. So in the individual branches, we could have stars and galaxies and broken translation symmetry. But the idea would be that fundamentally, this description of cosmology gives you a translation invariant flat background and a translation invariant wave function. And so actually this basically means that there's not really a horizon problem or a flatness problem because we're assuming a symmetry in the construction. Another very interesting point is that you see normally inflation, the idea of inflationary cosmology is used to explain the existence of correlations between regions of the universe that we observe that seem to have, that would have never been in causal contact before without inflation. So if these O1 and O2 are far enough apart, then in the cosmology picture, it would be hard to explain why there might be observed correlation between, say, the temperature in these regions, because even if you extrapolate all the way back to the Big Bang, their light cones don't intersect, okay, unless you add on an inflationary region. But actually, in this picture, in this model, you see that because the 2-point function in the cosmology is equal to the 2-point function in the wormhole spacetime, and the wormhole spacetime is static, so it just was there forever. It's actually natural that you would have correlations between operators at arbitrary separations. So this framework seems to explain the correlations at all scales without actually invoking inflation. Another general prediction here, just from the setup, we were able to describe spacetimes as long as they were time symmetric. And so if we're going to use this setup, then basically a prediction is that you're going to have a time symmetric cosmology. Okay. And as I emphasized at the beginning of the talk, we can't really know just from observations in our universe, we can't be sure that the cosmology is not going to recollapse at some point. Okay, so perhaps it's even consistent with our observations. Okay. Now, one of the really interesting things is that even though we assumed lambda less than 0 in these models, and so it might seem like from the start we're just talking about some cosmologies that are not realistic. As I'll now explain, it turns out that in these models, actually having time-dependent scalars or time-dependent dark energy is a generic feature. And it's not very hard to actually get a phase of accelerating cosmology before the collapse happens. Okay, so it may actually not even be out of the question that this kind of model could describe fairly realistic kinds of cosmologies. So that's I think I'll be able to finish in a few minutes. That's the last thing I wanted to explain. Why do you get this time-dependent dark energy, and where does it come from? Okay, so let me just go back and remind you that our starting point was some three-dimensional CFT, and this thing is dual. Before we couple it to anything, this would be dual to some asymptotically ADS4 spacetime. Now, usually the kinds of gravitational theories that we'd have in string theory constructions, they would have gravity as well as various other fields, and typically they have a number of scalar fields. The scalar fields in the geometry have masses that are related to the operator dimensions in the dual CFT. And in particular, some of these scalar fields often have negative mass squareds. Okay, so that's okay in ADS spacetimes. It can be stable as long as the negative mass squared is not. These scalars with negative mass squareds, they correspond to operators in the CFT that are relevant or marginally relevant. And if you look at the most generic kinds of solutions of these effective field theories, if you look for the most generic kinds of asymptotically ADS solutions, then those specific scalars with negative mass squareds, they typically will have a non-trivial profile. So setting them all to 0 is a special case, and you can use that to just get the ADS4 solution. But there's a lot more solutions, generally speaking, where asymptotically you still have ADS4, but then you also have these scalars that go to 0 at the boundary. Okay. And the way to interpret that from the field theory point of view is that when you have these scalars that are going to 0 at the boundary, that corresponds to saying that your field theory is only strictly a conformal field theory in the UV. And if you go down to the IR, there's some relevant operator that becomes important, and these relevant operators are in one-to-one correspondence with the scalar fields that you would have in the geometry. Okay. So in fact, most of the solutions in this framework, we would expect to have some scalar fields that depend on the radial direction. And in the cosmology, those scalar fields would depend on time. Okay. To understand the physics of those scalar fields, then we just have to write down the equations of motion for the scalar field and the cosmological background. These typically back react, so you need to consider coupled equations between the scale factor and the scalar fields. And an input here is the potential for the scalar field. So for these ones that are allowed to turn on, that correspond to relevant operators in the CFT, the potential goes downward at the start because it's a negative mass squared. But then typically the whole thing would be bounded below if the theory is stable. So typically there's also interaction terms, and altogether we would expect the potential to end up being bounded below. And so it's natural that even though you have a negative mass squared, eventually the potential becomes positive. Okay. And the solutions then you can understand in terms of this potential. So the scalar field equation actually just looks in the wormhole solution like the evolution of a particle in this potential, in the wormhole it's the inverted potential. And so what happens is that typically the scalar field would go to 0 at that asymptotically ADS boundary. Okay, so whatever this negative value of the potential, and then as you go inward, it rolls down the potential, and the whole thing is time symmetric. So this is the behavior of the potential as a function of position in the wormhole geometry. Okay, and the scalar goes out and then it comes back. In the cosmology, we've got the evolution of the scalar field from the Big Bang to the middle is like the motion of the scalar in this potential, and there's some damping which is provided by the Hubble. The Hubble constant gives you a damping term. So a typical kind of behavior there would be to come down, go up here, and then head back up. Okay. Now, depending on where you start, you might start here, go down, go back up, and then that would say your cosmological constant would, or your dark energy would be negative all the time. But another possibility is that you start up higher somewhere in the positive region and then come down and then go back up. Okay, so a fairly typical situation would be that the potential energy of scalar fields, it would start at a large positive value. That could cause acceleration. Then the scalar field over here, the potential drops to a negative value, and then you get a crunch, and then you have the time reverse of that. Okay, so it's like quite natural to have scalar fields that are time dependent. That says in these models, typically your dark energy will be time dependent. And in at least some cases that are not particularly special, that time dependent dark energy could be positive early on and then only later become negative. So you can get acceleration. Okay, so that's all I wanted to say. Just as a summary, I argued at the beginning that if we want to understand microscopic models of cosmology using string theory, it's maybe a good idea to focus on the negative cosmological constant cosmologies, because that's the place where we have the best understanding of quantum gravity. I then argued that actually we can give a description of some negative cosmological constant models of cosmology using fairly standard tools of, that should say, holography. And the idea there was to use holography to define a Euclidean gravitational theory, and then use that to define a special state for the wave function of the universe, like Hartle-Hawking. An interesting feature of these models that was unexpected, to us at least, is that they can fairly naturally actually have a phase of accelerated expansion, even though the cosmological constant is negative. And also, they fairly naturally explain some of the things that usually require inflationary cosmology to explain. Horizon problem, flatness problem, existence of correlations at large scales in the universe. So it will definitely take more work to understand how realistic these models of cosmology can be. And that's something that we're focusing on now, going forward, trying to study some specific examples. So thanks for your attention, and I'll be happy to take questions.
Thank you very much, Mark, for such a nice presentation. Two participants have raised their hands. Can you please unmute yourself and ask? Supreet, do you have a question?
Yes, thanks.
Yeah, please.
Thanks, Mark. So just one question. So it's nice to see that you've got sort of getting both the late time acceleration as well as something that can, leave away inflation. So do you have any thoughts on the scale invariant power spectrum that we usually use in cosmology coming from inflation?
Yeah, this is a really good question.
How that may arise in your model?
Yeah, indeed. So one thing we're looking at, if you want to understand the power spectrum in cosmology, then it should be something you can extract from if you can calculate the 2-point function of the electromagnetic stress energy tensor. So in these models, the simplest place to calculate that would be at this later time when the universe recollapses. And in order to calculate this 2-point function of the electromagnetic stress energy tensor, then the simple thing to do would be to try to calculate it in this wormhole background. Now, this thing should be related, again, by the correspondence. One should actually understand this 2-point function in the wormhole as coming, one could relate it to some 2-point function in this underlying like coupled 3-dimensional quantum field theory. And so we haven't done this calculation yet, but I think it will be very doable in the model, and we should just be able to understand whether it looks anything like the actual power spectrum or whether it's completely different. So it's sort of encouraging that underlying this calculation is some kind of conformal field theory, and so it may be in a sense natural that some scale invariance or well, see, this isn't quite a conformal field theory because it has this RG flow. But yeah, I mean, maybe there's some underlying scale invariance there, but I don't know yet. Basically, that the answer is that we think we know how to do the calculation, and we're working on it, and it will be interesting to see if it, how realistic it looks.
Yeah, that would be interesting. Thanks so much. Yeah, I guess that would be some sort of a scalar QAD calculation or something, or.
Well, I mean, we could actually just have a regular electromagnetic field in this background,
okay,
or just do a scalar calculation. So the answer is going to depend on what is our effective field theory, and so maybe as a toy model, you could just study a scalar field with a background, but you could also, if you wanted to, try to study some electromagnetic fields.
Sure. Thanks so much.
Yeah, thanks, Suprit, and thanks, Mark. Any other questions?
Can I ask something, Sumanta?
Yes, please go ahead.
I didn't quite get how you get the cosmological scale factor as a function of cosmological time from the wormhole picture.
Yeah, so it's just essentially just it's just basically this analytic continuation. So so the first thing would be to find the Euclidean scale factor in the wormhole geometry. And you could either think of that in the 4D effective theory, just trying to find this wormhole solution, or it should also be extractable if you were able to, if you could calculate quantities in the dual CFT, you should be able to understand what this scale factor in the Euclidean wormhole spacetime is. And then it's simply the cosmological scale factor is then simply replacing tau with IT. So it's just a simple analytic continuation.
No, that's okay. The other one I'm saying, the Lorentzian one. How do you get the cosmological scale factor from the Lorentzian wormhole picture?
Oh, I'm sorry. Oh, yeah. So these are the same function. This analytic continuation is basically trivial. So you just have dx squared here, and then here we replace one of those coordinates with time. So the scale factor here and the scale factor here are actually exactly the same function of tau. And again, you could try. It could come in effective field theory by just trying to find the relevant solution of the gravity coupled to this matter. I should say that there's an interesting. I didn't have time to mention it. There's an interesting aspect of this Lorentzian picture, which is that in order to get such a space-time with two asymptotically ADS regions, so it's like a traversable wormhole. And if you look at the Einstein's equations, supporting a space-time like that actually requires some negative energy. And this is, I mean, it sounds unusual at first, but here we're talking about a space with two boundaries, and then we have some quantum fields on this space-time. So those things will have some kind of Casimir energy. And it's fairly common with Casimir energies to have negative energies that are the right type of thing to support the wormhole geometry. In order to get a sufficiently large wormhole, you need something a little bit, you need sort of quite a large amount of this negative Casimir energy. And so one of the interesting things that we explored recently was just in some holographic toy models, asking the question for some CFT with two boundaries and considering lots of different boundary conditions. What are the possibilities for the Casimir energy? And we found actually that in some class of models, we could make it as large as and negative as we want. So it does seem like with the right choice of boundary physics, you can have the appropriate kind of negative energy here in order to support this wormhole.
Yeah, but in the wormhole picture, the AE square in that metric is a function of tau, right?
Yes.
So that's not cosmological time.
Yeah, but it's the analytic continuation of cosmological time.
Ah, so it will not work for any scale factor as such, right?
Yeah, I mean the scale factor is going to be determined by the dynamics somehow, and then we need to it's time symmetric, so it should be some function of tau squared.
Yes.
And then you just have to replace the tau squared by minus t squared, and that gives you the cosmological scale factor.
Okay, thanks for the nice talk.
Yeah, I mean, here's
very much. Yeah, thank you very much, Sam and Mark as well. So any other questions from the audience? Any other question? Okay, if not, may I ask you one more question? Yes. So in this A of t expression, as Supreet asked at the beginning, that when you take square root, you said we should get t to the half. But I really do not see how, because the cosine has an expansion which is 1 minus t squared. So if you take square root, I can only get t. How can you get t to the half? Can you kindly explain?
So my coordinates are defined to be 0 at the middle. So if I take t equals 0 here, the Big Bang is at t equals minus pi over 2h. And so if I want to use regular coordinates where t equals 0 at the Big Bang, then you get square root of sine ht. And then the expansion around t equals 0 would give you square root of t.
Okay, thank you. And second thing is not quantum gravity supposed to solve the Big Bang and Big Crunch problem, but it seems that you are assuming this should happen in quantum gravity model. So if I ask the naive question, like what happens at the Big Bang, it seems there is no answer.
Yeah, very good question. So it's, indeed, it's challenging to, I think, this is one of the places where it's probably most challenging to extract the physics. So from this equivalence, as actually the observables at this late time are kind of equal, and then to get to the Big Bang or Big Crunch, then I guess in principle you can just use the analytic continuation, and I think if one had full analytic control over the observables here, it should also tell you exactly what the behavior of things as you go towards the Big Bang and the Big Crunch. So I think in principle, the answer is there, but it's a little bit, it's probably the most difficult part of the geometry to probe, because then it involves extrapolating all the way back to the early times. From this higher dimensional picture, I think it's interesting just to point something out, that here the Big Bang and the Big Crunch, they're in a sense identified with the past and future singularities in a black hole. And so this is also a question with ADS-CFT. We can describe black holes or two-sided black holes fairly well. And again, we expect that quantum gravity resolves the singularity in some way. But it's a little bit challenging to say exactly what is happening at the singularity using ADS-CFT. So I think in principle, this model would give some description of what happens at the Big Bang or the Big Crunch, but some technology is required to understand how do you ask that question.
Okay. Yeah, thank you very much. I think there is one last question for you. This is from Kinjal, who has raised his hand. Kinjal, please unmute yourself and ask.
Okay, thank you. Thanks for nice talk, Mark. So I have this question that it appears that your construction is being discussed for the late time acceleration of the universe. That is a quintessence kind of model of the dark energy.
Yes.
But at what stage we should start calculating things to match with the inflationary thing? Why inflationary discussion become important over here if we are concerned with late time acceleration?
Yeah, so right. So my discussion here, where the scalar would be here and then roll down. Yeah, indeed, I was trying to explain why there might be some late time acceleration in the universe. If you extrapolate further back, then I mean, naively, the scalar can become larger and larger. But you know, I mostly understand what the potential should look like. So here the values are like cosmological constant scale. So these are very small energy scales, and so one might expect if you go extrapolate backward in time enough that maybe at very early times the potential would be very large and could be closer to the Planck scale and could give you some inflationary physics. But I think this is not obvious that should happen. So one possibility is that, you know, maybe your potentials in string theory could be very complicated, and maybe you have some inflationary period and then some later acceleration period, and then the cosmological constant becomes negative. But it's not clear. Maybe you don't have inflation, but it seems like in these models you maybe don't need the inflation. So if you know, if somehow just the correlation functions in this picture, I mean, they seem to be not requiring you to know anything about the inflationary potential or the Big Bang or the early universe in order to calculate those things. So using the model, you don't need to know about whether or not there's inflation in order to calculate the perturbations. And so it seems that, you know, even if it did happen in the cosmology, you don't need to know that it happened. You can still find out the consequences just by this duality, by the calculation in the wormhole.
So that I understand that you can calculate from this thing, and you probably may get some kind of scale invariant, which may or may not be the case. But whether even if you get the scale invariant power spectrum, would that be a statement that there was no preceding inflationary phase?
Yeah, maybe not. I mean, so I think there's two options. One of them is you do this calculation, you find some reasonable spectrum, and then maybe it's like a dual picture. Maybe there was maybe in this picture you would say, oh, inflation generated these perturbations, and you have one way of calculating it using inflation. And then in this picture, you have a different way of calculating it, and it just gives the same answer because it's some kind of duality. The other option is maybe in this picture, there is no inflation, but you still have you know, the kinds of things that inflation normally predicts for some other reason because of this connection to the vacuum correlations. So I don't know which one of those it could be. I mean, it could, of course, a possibility is you calculate the perturbations here and they're totally unrealistic, and you know, then this is more like a toy model of cosmology that's not relevant for our universe.
Okay, thanks.
Yeah, thank you very much, Kinjal, and thanks to Mark. I think this will close this session. So I thank Professor Mark Raamsdonk and as well as the previous speaker, Kate Jacobson, for such a nice first session of today's conference.